So it works?
Is it working?
Is it working?
Yeah.
Okay, good, thanks.
Okay, so it's my great pleasure to introduce Hongseok Yang, who's worked with Peter for a long time and was one of the authors of some of those early seminal papers. And he's going to talk about parametricity and the influence that side.
So thank you very much. Thanks a lot for inviting me to give a talk in this wonderful place. And then, when Jules asked me to give a talk, he said, I can talk about anything. And then when I look at the list of the topics of the talks, they are mostly about separation logic and so on. So I want to talk about something else, which is what Peter did during perhaps his PhD and right after his PhD, which impressed me quite a bit. So I have two messages of my talk. The first message is that, even before separation logic, Peter wrote many wonderful papers. Actually, I'm going to talk about one particular paper of Peter, which is still my favorite. I think for me, it's the best paper in my life. So that I would say, the reason I talk about it is because, if you haven't read Peter's old papers, I recommend, and then also if you have some time, I recommend to have a look at it. The second message of my talk is that maybe Peter's works on parametricity, although it's done in the old days, and also it kind of solved many important problems at the time, might be relevant to this modern era of deep learning. So I want to talk a little bit about how it's possible connections. This is not related, it's more like after receiving Jules' invitation, I thought about what I want to talk about, and then I don't have any result, but maybe some vague observations. I just want to talk about this observation, which Peter might like. In my life, when I met Peter, I was, just like now, I have perhaps some feelings, but I couldn't quite formulate why I feel a certain way, and I couldn't put those feelings into the right words. But Peter somehow knew much better about me, much better than I do. And then he kind of rephrased my thinking. So maybe he will do the same after my talk. Okay. So my talk has a two-part. The first part is a little bit somewhat old story of mine. Okay, so I was a PhD student. Uday is not here, in Urbana-Champaign from 1996 to 2001. And Uday was a very close friend to Peter O'Hearn. And then Uday at that time said, okay, let's have a reading group. So Uday, I, and then two other students, Brian Dunphy, Howard Huang, we read these papers in these two volumes, which are edited by Peter O'Hearn, and then his former supervisor, Bob Tannen. And then these books are, here's a list of papers in the first book. Then there are 10 papers. And then there are another book. There are 11 papers. Steve Brooks also have a paper in the book. And papers in those two books are about higher order imperative languages. And then, there are some papers which are about the design of higher order imperative languages. Some papers there are quite a lot of papers which focus on the semantics issues. And I really liked it. And then during this reading group, I learned so much about some very basic techniques like a functor category semantics and so on that really helped me. Maybe I use it sometimes, I didn't use it some other period of my career, I've mostly focused on some different aspect of programming languages, but it just remained with me for forever. And it still have a kind of big influence about how I think about many things in programming languages and some other area. Okay. And then among all those papers, some we covered together. So we sat down and we read those papers together. And of course, as a fresh graduate students, I couldn't quite understand anything. But then Uday, after some paragraph, Uday somehow explained the key idea behind the paragraph and so on. So that really helped me quite a bit. Okay. And then some other papers I take a time. I spend my own time and read those papers. And there's one paper that I liked really a lot. That was this paper by Peter O'Hearn and Bob Tannen. It's parametricity and local variable. I think the paper was originally published in POPL a long time ago, maybe 30 years ago. And then it was later published in JACM. And then then it appeared as one of the papers in this volume. And there are several, at that time I really liked it. And then there are multiple reasons I liked the paper. And one of the reasons was a bit silly. It has a very long introduction, but surprisingly, at that time I was a fresh graduate student. And I couldn't, whenever I read the introduction of any paper, I couldn't understand anything. But this paper has a very nice introduction, which even I, like who knew almost nothing about programming languages, was able to follow. And then actually after reading the entire introduction, I was kind of see what Peter was doing in the paper. So that was a long, but it was very engaging and kind of exciting introduction about what Peter did, and also about the area of local states and parametricity, which I really liked. So maybe because I got so good impression at the time, this paper still remains as one of my favorite. And the second reason is that it kind of revealed very deep connection between local state, which has been the main topic of study among the semanticists at the time, and another big concept in programming languages, which is called relational parametricity. So I mean, maybe some of you already know it. Like I think Derek worked on it in one way or another before. Of course, Peter and a few others. But maybe now some of you met Peter after separation logic, doesn't really know. So I'm going to explain a little bit about what happens in the paper. So think about the procedure that you look at on the left-hand side of the screen. That procedure has a global, that program has a global procedure called capital P, which cannot really access the locally declared variable z directly. And locally declared variable z can only be accessed via two parameter. Okay, so the first, by the two procedures provided. Okay. Yeah, so the first procedure is called increase. So that's increase the value of the local variable z. The second procedure is a val, which returns the value of the variable z. And then z is initialized to 0. And this global procedure P has this inc and var as the two parameters. So intuitively what really happened is that the local block essentially define a counter object, and you pass two methods of the counter object to global procedure P. And because this global procedure P cannot really access the local variable z, this program is actually equivalent to the program that you see on the right-hand side. Exactly the same, except that whenever we call the increase method or increase procedure, instead of increasing the value of local variable z, it decreases the value. But whenever we call that the procedure P calls the val, which is the value of the counter, instead of returning the value directly, it negates the value. So essentially from the outside, you cannot really tell the difference between the two. So the idea was, how can you come up with some semantic account of the local state that can validate the equivalence between these two programs? So that was one of the big challenges. I mean, that and many other things, many other nice examples by somebody called Meyer and Jeebers. I mean, validating those examples and providing the semantic account of local state was one of the big challenges at the time. And then Peter's observation is that actually it has something very related to the John Reynolds relational parametricity. So I can't really explain the entire thing exactly, but I will give you some flavor of what the relationship is. So in the Peter's account, this global variable P can be understood. So the main message is that non-local procedures are independent with respect to the local state in a way that they are relationally parametric with respect to the local state. So that was roughly the idea behind the intuition. And then some way to look at it is to understand this P as just intuitively can be understood as this kind of parametrically polymorphic functions. It's parametrically polymorphic with respect to type parameter beta, which represent the local state of this integer variable z. So you say that whatever beta is, if it receives two methods, the first method is mapping from beta to beta, just like an increase method. Second method is it takes the value of the beta and return the integer value. And then this P will become a state transformation where alpha represents the global state, beta represents the local state. And then the key insight is that this procedure P is, the way it behaves, the behavioral procedure P is essentially relationally parametric with respect to this type parameter beta. So the left-hand side, you can understand it as an instantiation with the integer z, but the increased part plus, and then the value is just identity. The other side had essentially what you see on the screen. Okay? And then based on these observations, he was able to bring the Reynolds relational parametricity in this context and came up with a semantics that was able to validate many of the challenging equalities between the two programs, which in a sense reveals the characteristics of local states at that time. So that was really nice. I mean, for me, I didn't know about the local state. I knew a little bit about local state, knew a little bit about relational parametricity, but Peter kind of make a really nice connection between the two. But the reason I really liked a lot about Peter's work is because, I mean, the way he did it was he came up with a very generic framework, which is called some categorical framework, which if I try to explain everything, I don't think either you already knew it or you will never be able to understand in like 10 minutes talk. So it's a categorical framework involving two categories, so-called G, V, G, E, and three functors, G, delta 0, and so on. The rest, you don't have to remember anything, okay? But it's a categorical setup. One way to understand this is it's a categorical setup, which you can use it to understand the uniform families of functions. It's not just a family of functions, it's a uniform family. So it's like relationally parametric functions can be understood as a family of functions for each type parameters. The important bit is that it has to be uniform. It should behave, in a sense, the same way. And then Peter's framework allows us to capture this uniformity. Categorically, his framework captures this uniformity by two concepts. One is called naturality, coming from the category theory. The second is coming from this extra structure in his setup, which corresponds to something called relational parametricity. I think that's perhaps like a Uday's terminology. Uday used to call it this first part as a parametricity, the second is naturality. So his framework captures uniformity by these two concepts. Again, you don't need to understand. If you know about them, great. If you don't know, doesn't really matter. I'm going to tell you a little bit about it in the context of deep learning later. And then now he used this framework to define the abstract account of the local state, which I thought is great. The framework is really nice. And then looks like it fits everything together really, really nicely. And furthermore, according to my understanding, maybe some other person who are much better than me in the semantics maybe can explain the kind of follow-up work based on this reflexive graph of categories. But my understanding is that they had some big kind of, at least reasonable amount of influence on the work on the modeling of relational parametricity. But for me, I mean, this kind of became a part of my thought process. So whenever I try to solve some similar problem in a different area, it starts to play an important role. So that's what I'm going to talk about next. So not for parametricity, but we can understand it as a categorical setup, which can be used to define the uniform families of functions. And it turns out it might be have some relationship to addressing some issues in deep learning. So that's what I want to talk about. I want to talk about some particular problem first, called the fixed input dimension problem of neural networks, and then I want to tell you a little bit about how this Peter's framework can be used to address some of these issues, or think about these issues perhaps in a different way. So what the problem is? Here's the problem. So think of typical neural networks. I mean, although not all the neural networks, typical neural networks assume the dimension of the input and dimension of the output. So in the screen, you will see a function f that goes from dimension of input n, the input dimension is n, output dimension is m. What does that mean? That means if you learn a sorting algorithm using the neural networks, it is able to sort 100 elements. But if you give a 200 element, it doesn't really know what to do. Okay. There are neural networks called RNN, which works for inputs of arbitrary dimension. But usual neural networks assume the dimension is fixed. So that's a bit problematic, because if you think about the algorithm, like sorting algorithms, also any algorithm in the graph, they work on the graph of arbitrary size, and the sorting algorithm, number of items doesn't really matter, and so on. Okay. So there's a kind of big difference between what's really going on in the neural networks and then what's really happening in the algorithm. Also, in the mathematical function, if you think about inner products, we never say inner products work on dimension 3, but it doesn't work on dimension 4. It works on dimension 3, dimension 4, dimension 5, and so on. And in some sense, what they are doing is the same thing, and it do the same thing for arbitrary dimensions. So the question becomes, how can you come up with neural networks that can work on the inputs of arbitrary dimension? At the same time, we can train it with a finite dimension. Because when you train on neural networks, you cannot really train the neural network with dimension 1, dimension 2, dimension 3. That's going to take an infinite amount of time. So you want to have a finite trainability. At the same time, you want a neural network that works for arbitrary dimensions. Okay. So very recently, like last year, there is a work by, I think maybe some other people worked on this. So as I said, I don't have any result on this. It's just some observation I made last year. And then I just want to talk about it. Maybe Peter might or might not like it. But anyhow, the last year, there's a guy called Levin and Diaz. They have some idea. And their idea is that they want to think about this neural network that works on arbitrary dimension as a family of neural networks. Okay? But it's not just arbitrary family. It's a uniform family. So their strategy works as you see on the screen. They consider a family of neural networks, Fn, theta n. So subscript n means it works on some input dimension is related to n. That can be n or n squared and so on. And then theta n are parameters on that particular input dimensions. And then instead of thinking about just arbitrary family, they think about uniform family. Okay, I'm going to tell you what kind of uniformity they assume. They consider uniform family. And then the third point is actually quite important. The third point is say that now they want, in that specific architecture, they find some n0 such that, the uniform family is for arbitrary n. But if you have a family, uniform family up to n0, okay, then it can be uniquely extended, the uniform family for arbitrary dimension. So what that means is this uniform family up to n0, in a sense, captures the entire information about the family for arbitrary dimension. Okay, so and then once you identify n0, then you can train the neural networks from dimension up to n0 using n0 dimensional inputs. I didn't tell you exactly how they do it, but that's how they do it. And then once you learn it, then you can use this the result in the third point to extend the neural networks up to dimension n0 to arbitrary dimension. So that's roughly the setup that they have done. And then the one possible question is, you might ask, it looks like things are all reasonable except the third one. It's a bit like some finite model property in the decision procedure. So you have some finite n0, then you learn it, then that can be uniquely extended to arbitrary dimension. This cannot ever happen. It turns out it can happen and then there are a few ingredients, but one of the key ingredients is uniformity. Okay? Because instead of thinking about arbitrary family, we are thinking about uniform family. This extension is possible. Then what kind of uniformity they considered? So they called the first uniformity as compatibility. I'm going to give you explain it with a specific example. So Fn is taking n by n matrix, and then you return a real number. Okay. So if n is 10, it takes a 10 by 10 matrix. N is 20, it takes 20 by 20 matrix, and so on. What they call compatibility is say for every n and m, where n is smaller than or equal to m, this commutativity diagram that you see on the screen works. Then what the commutativity diagram says is that running Fn for say 10 and running the functions for dimension 20 are related by the diagram, where this mapping iota nm is really taking a matrix, 10-dimensional matrix, 10 by 10 matrix, and embed it 20 by 20 matrix by just adding zeros everywhere. So it's called zero padding extension. Okay, so that's the idea. But if you are familiar with the parametricity and so on, this looks very much like a naturality condition. And you can actually formulate it as a naturality condition. And then actually the uniformity condition has another aspect. So how much time I have? Very little, right? 5 minutes left. So there is an exercise I prepared, but I think I can skip it. So this exercise, the solution is 1 and 2. The third one doesn't satisfy this condition, okay? But the second condition is called equivariance. So in this specific context, specific example, they considered permutation groups, so any permutation from 1 to n. And equivariant means that now, if you have two matrices, they are related by these permutations. Then if you map it by the function fn, they have to produce the exactly same output. And that's related to what Peter called parametricity conditions. Like a reflexive graph setup, the extra parametricity condition can be phrased in this way. Okay? And of course, I mean, I'm going to tell you later, they use a functor category to formalize this, but I'm just saying the Peter's framework can also accommodate and maybe give a more general idea about what's going on. Again, the exercise, the solution is number 1, but I think I'm almost done. My time is almost up. Okay, so in that setup, then it turns out we can find this N0. I said that in the entire scheme, the most difficult part is get some kind of finite representative, well, some form of bound on finite model property-like thing. Okay, and it turns out if we set N0 to 2, then it works. And under the assumption that instead of thinking about arbitrary family of functions, we consider uniform family of linear maps only. Okay, so if you consider uniform family of linear maps, then N02 works. That means if you have a family where the elements for like the 1-by-1 matrix, 2-by-2 matrix, I know what to do. The family is uniform and all the functions are linear. Then it can be uniquely extended to the uniform family of Fn, which are also uniform and the linear map. Okay, and so in this case, this N0 actually exists equal to 2. And it turns out this kind of phenomenon happens quite often. And around 2010, in algebraic topologists, they worked on something called representation stability. They work on, maybe in their context, they consider like homology and so on. In this case, they worked on the representation of groups, and then it turns out this kind of phenomenon happens quite often. Okay. And as I said, how it's all related to Peter's work, then although I'm not showing you the Peter's frame, this Levin and Diaz work can be formulated in the Peter's framework for parametricity based on reflexive graphs. And I said in Peter's framework, uniformity is captured by parametricity and naturality. And the compatibility condition they correspond to the naturality condition. Equivariance conditions can be captured by the parametricity condition in Peter's framework. But why do we want to do it? I don't know. But perhaps because just like in the parametricity, maybe because Peter's framework has many nice structural properties, at the same time it's more general, it may suggest a new way to generalize what Levin and Diaz and other people are trying to do to solve this finite dimensional input problem. And in the machine learning jargon, in parametricity, we say, by changing some notion of relation, we can strengthen the notion of parametricity and weaken the notion of parametricity and so on. And that corresponds to so-called the strength of kind of changing the strength of the regularization in the context of deep learning. So maybe something like this can happen. Okay. So here are references of these two papers that I refer to in the second part of my talk. And then, so that's it of my talk. And finally, I want to say thank you very much for Peter. Yeah, so I think, as I said, I live reasonably comfortable life now, but I don't feel like without Peter it was possible. I was very not self-confident during my PhD, and I couldn't really explain my idea. So like Uday once told me, why don't you just stop and think before talk? But because like I couldn't really, I don't know what to say. But the Peter somehow, even though I didn't really think and talk, he somehow understood me perfectly. And he kind of told me, is that what you want to say? And then so, not just this, like throughout my career, he helped me in many, many ways. So thank you very much, Peter.
Time for one question, Peter.
Okay. So it's as if these deep learning folks are working in the topos of reflexive graphs?
No. So
is these FNs parametric natural transformations?
That's just my way of rephrasing this.
I mean, as if they are. They're not literally doing it.
That's right. But they are using functor categories. And it's actually representation stability is formulated with functor categories. Okay. Thank you.
Doing that without knowing it.
Yeah, yeah.